All right. Hello, everyone. Today is going to be chapter 2 of classical dynamics of particles. We're going to be going over the Newtonian mechanics of a single particle. So we'll see how far we get in it with the first video, since the last video is kind of long. If you haven't seen that already, it's up on the channel. So without further ado, let's get started. So for the introduction, basically, by this point, if you're reading this textbook, you're probably already familiar with the terms velocity and acceleration of a particle and the concept of mass. So basically, the point of this chapter is we're going to kind of see Newton's formulation for it. So let's get into Newton's laws, which we can just state simply as, this is straight from the textbook. First law, a body remains at rest or in uniform motion unless acted upon by a force. Second law, a body acted upon by a force moves in such a manner that the time rate of change of momentum equals the force. So Newton's second law is kind of how you learn in lower division classes, F equals ma. Then the third law is the equal but opposite one, which is if two bodies exert forces on each other, these forces are equal magnitude in opposite direction. So 2 might seem a little bit different. That's because it's in a different formulation than you've probably seen it in your classes, but we'll see that it's pretty similar. So in order to kind of see that formulation for the second law, we have to define a quantity, which is momentum. Momentum is defined as mass times velocity. So then we can express Newton's second law as F equals dp dt, which is equal to d dt of m times v. And we can say if mass is constant, right, well, derivative of velocity acceleration, so that's just ma, right? If mass is constant. Later on in relativistic courses and stuff where mass can change, and in other classes like that, you'll notice that you're going to have to do chain rule, and you're going to have like a m dv dt plus dm dtv, like that. So that's just something, so you know. And basically, we can get into, I guess, the third law, which basically says for two isolated bodies, force 1 is equal to the negative of force 2. In other words, if I push on a wall like that, the wall pushes back on me like that. So we can basically, you know, use Newton's second law and see what this looks like. So dp1 dt has to be equal to negative dp2 dt. So we can kind of expand and get m dv1 dt, if assuming again mass is constant, which again it does not have to be in a lot of cases, but for a lot of problems it will be. It's a negative sign there, sorry. In other words, m1 a1 is equal to negative m2 a2, or the ratio of the masses is equal to the negative inverse ratio of the accelerations. And this kind of allows us to kind of summarize Newtonian dynamics with these 3 laws. So good example of this is gravity. So we know F is equal to ma is kind of like the general equation, right? And we know that the weight force, which I like to write as force of gravity, is equal to mg, where the g vector, right, on Earth is 9.81 on Earth, meters per second squared, which comes from, we'll see, this second law. So basically there's 2 types of masses is kind of the point that we're trying to make here in the ma versus the mg equations, and that is that there is if it lets me screenshot, that is, there we go, is inertial mass and gravitational mass. So basically we've kind of come to this conclusion that we kind of observed stuff is attracted to the Earth, and that's the force of gravity, or the gravitational mass, which is the mass determined determining the gravitational forces between a body, and then the inertial mass, which is how resistant you are to an acceleration. And you're like, well, how can we only ever use one mass? And that's because of the principle of equivalence, which basically says these 2 are equivalent. And that's why we just call it mass, basically. So yeah. Another way to rearrange Newton's third law is if the time derivative of momentum 1 plus momentum 2 is equal to 0, that immediately tells us that P1 plus P2 is equal to constant. Now, this does not mean that P1 and P2 can't change. It just means that if P1 changes, P2 has to change in the opposite fashion as well to keep the total sum constant. And this is basically a way of writing the conservation of linear momentum. This is like a special case of the conservation of linear momentum, sorry. But we'll see what that looks like later. So now we can move into 2.3 now that we've had a general formulation of what Newton's laws are, which we should probably talk about the frames of reference. So, frames of reference, before I get into what the textbook says, I'll just say what I kind of think of it as, is basically you can't really make sense of anything if you don't have something to compare it to. In other words, you need some set of kind of standards or something in order for something to happen. In other words, you guys have all probably heard, I don't know, Discovery Channel, something that the Earth is moving like some hundreds of thousand miles per hour through our universe or whatever. I don't know the exact number. But I mean, I'm just sitting at my desk right now. I don't feel anything, right? And that's because it depends on your frame of reference. So a reference frame is called an inertial frame if Newton's laws are valid in that frame. So an inertial frame Newton's laws get a check mark. Good. Which we'll see, you're like, wait a minute, I thought Newton was all physics had to offer. Unfortunately, no, that's why we have general and special relativity, because Newton actually assumes time is an invariant quantity. But yeah, like time in all reference frames is basically the same as what he assumes. But anyways, and this is very different from like general relativity or special relativity. But anyways, we're here to talk about Newton. So, and Newton's laws, if they're valid in one reference frame, one inertial frame, then these are also valid in any frame of motion, any frame in uniform motion, so not accelerated. So I can have a frame here. In other words, let me draw it. A person standing still is in this frame, right? Now I have another frame over here where our person standing still is looking at this guy in a train car that's also standing still. But this is moving with a constant speed v compared to them. Newton's laws here and here are equivalent because it's a constant frame, because it's a constant speed. And this is called, what's it called? Galilean invariance, or the principle of Newtonian relativity. In other words, you might have heard this stuff before. This guy throws a ball. This guy sees the guy here throw a ball straight up. What does it look like for him? From his perspective, you know, if he has binoculars or whatever, he sees, those are terrible binoculars, he sees like the ball go like parabolic, basically. And that's what we mean by Newtonian. But you run into a problem when you ask what happens if you shine light, and then you find out the speed of light is constant, and then boom, you're Einstein. But not really. That's kind of special relativity where that goes to. But anyways, relativity basically shows us the concepts of absolute rest or an absolute inertial reference frame are meaningless. In other words, we don't really know, there is no absolute, everything is just relative to you around it. The same way me sitting at rest looks like to an observer outside in space that I'm moving 300,000 miles through the galaxy, right? In other words, we need to define our stuff in space and time. But okay, so let's look at an example of how you can describe your stuff, how you can choose your reference frame and all that. In this figure, we can describe the path of a free particle along the path AC, so from here to here, just in terms of, what's it called? Along the path, and rectangular course's origin moves in a circle. Oh, since it's moving in a circle, we cannot describe it in an inertial reference frame because there's some kind of acceleration, right? And that's given by the centripetal acceleration of the system. That's just an example of a case where you can't use an inertial reference frame. Okay, so in other words, Newton doesn't always work but if it's an inertial reference frame, it's a very good chance it's going to work. So, okay, let's go back to Newton's second law, which is dp dt. So then, by the way, I'm transitioning to 2.4. The equation of motion, let me erase that, write that back there, for a particle. So how does a particle move, basically? What happens to it? Well, we know that's the same thing as d dt of mv, which is just equal to m second derivative of its position vector, right? Time derivative. So dots signify a time derivative, and again, we're assuming m does not vary in time. So what we could do then is we can realize this is a second order differential equation that can be integrated to find, the position function r equals r of t, and we can do that. And then what we basically want to do is we want to find a general case for this. So for a given dynamic system, we normally know r and v as functions of time because we can experimentally measure this. So then they basically give us just 5 good steps to solve problems. So these are your general problem solving tips. Is, as usual, as I said in my last video too, always draw a picture. I think it's really useful. Write down the given quantities. It's good to have them right there on the screen or paper. Write down your equations and then think about what you have to do basically, and then just plug in. So we're going to go look at a more simple example that you've definitely seen in your lower division classes. What happens if we have some block on an incline, right? Well, we draw our pictures right. We see the normal force acting upwards, the force of gravity downwards. We see the components, and then we align our coordinate system along the direction of motion, so x points in the positive direction, and then you basically just solve. So I don't think it's worth going through this example since it's pretty easy, but I suppose we can. So let's just go through it, I guess. So the net force, I like to write it as sum of the forces is equal to force gravity plus normal. Well, I write it as sum of the forces is 0. So then, and then also force net, or I guess it's not 0, it's equal to MA, sorry. MA, where the sum of the forces is again equal to the force of gravity plus the normal force. Personally, I would write this as N minus mg and so forth. But anyways, so we can do it in the y direction and the x direction. So let's do sum of the forces. I don't like how the textbook does it. In the y direction is equal to 0, and it's mg cosine theta negative plus the normal force is equal to 0. So then n is equal to mg cosine theta, and then we can sum the forces in the x direction. And now the x direction is our direction of motion, so that's equal to ma, which is, again, mx double dot. And that immediately tells us that x double dot is equal to mg over m sine theta, right? Because we're assuming there's no friction. So we're in this case right here. I guess they draw friction here, but I guess we're not including it for now. If you did, it's just mu mg sine theta. But anyways, that tells us then that that's equal to g sine theta. And you've probably gotten equations like this where a is equal to g sine theta plenty of times. That's kind of problem. But now let's think about it. So if we assume 30 degrees, that means x double dot is equal to g over 2, which is 4.9 meters per second. And now we want to get our equation of motion, right? So we can find the velocity of the block after it moves from rest at difference x naught, basically by doing 2 x prime, first derivative is equal to x g sine theta. Notice it's just the exact same formula. We just multiply by 2x. And now we can basically do the time derivative of this. We get d dt of x prime squared, or x dot squared, is equal to 2g sine theta dx dt. And we can integrate from basically 0 to v naught squared of the derivative of x prime, oops, sorry, square should be inside, and that's just 2g sine theta from 0 to x naught dx, or this is just x naught. And we can plug in our knowns, which our knowns are at t is equal to 0, x is equal to the velocity, which is equal to 0, and then at t is equal to t final, x is equal to x naught if it goes a distance x naught, and x prime is equal to v naught. So then v naught squared is equal to 2g sine theta x naught, or v naught is equal to the square root of that. And there you go, that's a simple example of how it works. And then the next example, they include friction, and you can do that on your own. But okay, so something they want to emphasize is the effects of retarding forces. Where basically the force F in equation 2.7 is not necessarily constant. And let me write down equation 2.7 for you. 2.7 is F is equal to d dt of mv, which is equal to m r double dot. In other words, this force does not have to be constant. Okay, so let's kind of see what that means. In other words, we can write our force vector as let's say we're in the gravitational field, so it's the force of gravity plus our retarding force, and that's just equal to mg plus force r of v. A good way of saying is, probably a great example of this is, we all know in easy physics problems, right, we like to drop something and we just ignore air resistance, right? Well, it turns out force drag is proportional to some constant times velocity to some factor, basically. In other words, the faster you're going, the more force you feel. And you can see a great example of this of go drive your car, stick your head out the window, and accelerate, and you'll see at higher speeds you're going to feel a lot more wind. And that's just because of the random motion of particles in the air, and if you're moving faster, you're going to hit more of them, like you're going to be more likely to hit them, right? At a faster rate. So there we go. So, okay, I'm going to use the textbook's notation because they say, this is just off memory, they say the retarding force is proportional to v to the n, which you can see is the same thing right here. I just have a factor, and like I use v to the gamma, whatever. So we can use the power law approximation, and that kind of just tells us that the force then is equal to mg minus mk v to the n v over v. Whereas velocity is a vector, that velocity v over v is the unit vector in the direction of v. So yeah, I guess. And I guess they give you values for the small object in the air, but basically this is just drag and stuff. And if we want to basically calculate the real drag force at a more complicated, this is probably air resistance, probably more accurate. Air resistance. The real drag force, it gets more complicated, and we have the Prandtl expression. Prandtl expression, where W is equal to 1/2 coefficient of drag, density, a v squared cross-sectional area, and v squared. A is the air density. So yeah, basically you don't really care about it until you get to higher speeds, because then it really starts to matter, as the v squared term adds a lot. This is the drag coefficient, it's just the number you look up in a table basically. But anyways, okay. So, and then they have some examples of, well, I guess we can do example 2.1. Let's say we have a bullet we're firing, and bullets can go pretty fast, so it's going to experience air resistance, right? Or a resisting force kmv. So here they put n to the power 1 because for air it's basically 1, apparently. Although I've also seen models of it squared, so, or to the 3/2. But anyways, so that tells us then that ma is equal to m dv dt, which is equal to negative k mv. So immediately you see a situation like this. What do you think? Okay, let's get the v with the dv, and let's put the rest of the dt basically. So now I have the integral, oops, that's a highlighter. Let's get the integral of dv over v is equal to negative k integral of dt. So that's just, well, integral of 1 over x, right, is just ln of x. So ln v, yes, there should be an absolute sign, but it doesn't really matter. Negative kt plus c. In other words, we need to find out what c is, right? But we know the integration constant, we can figure it out because v at t is equal to 0 is equal to v naught. So therefore, the constant c has to be equal to ln of v naught, or v is equal to v naught e to the negative kt. Another way of doing this is you could just put this in from v naught to v and get the same thing, but whatever, if that makes sense. And then you integrate, from 0 to t, and you get the same answer. So that lets us, when we exponentiate, v is equal to v naught e to the negative kt. Okay, great, but we want, again, basically r of t or x of t in this case. So, well, v is equal to dx dt, which is equal to v naught e to the negative kt, right? So x is equal to v naught integrate e to the negative kt dt, which if you integrate e to the x, just e to the x. So it's just equal to negative v naught over k e to the negative kt plus another constant, I'll call that c2. But we know that at x at t is equal to 0 is equal to 0, so then c2 is equal to v naught over k by the same analysis. So x is equal to v naught over k, 1 minus e to the negative kt. What I want you to notice is this is a decaying exponential, so as time goes on, right, we basically have a what's it called, a decaying exponential. So it asymptotically approaches v naught over k as t goes to infinity, which kind of lets us define the terminal velocity. The terminal velocity is, if you've ever seen videos of people skydiving, right, they fall and they don't just keep going faster, right, or else you just, like, a parachute's not going to help you if there's no such thing as like a terminal velocity. But okay, we can also get the exact same thing by noting that dv dx is just equal to dv dt. This is chain rule, by the way. Dt dx, or you can also just see that you can think of it as just multiplying dt over dt, but it's chain rule in calculus, which is just dv over dt times 1 over v. So therefore v dv dx is equal to dv dt, which is equal to negative kv, and we can just cancel stuff out, and we get dv dt is equal to negative k. I probably shouldn't have canceled it out like that, but the v cancels. Dv dx is equal to, well, that's fine, I can leave like that, that's fine, as long as you know it's not in this equation, but whatever. Is equal to negative k. So then again, if we just integrate this, we get v is equal to v naught minus kx. In other words, the velocity decreases linearly with displacement. And the reason why it decreases linearly is because we go back to our assumption right here. It was our resisting force is kmv, in other words, v to the first power. It would not decrease linearly if we had some force proportional to like v squared or something. But anyways, okay, excellent. And so then they have other examples, and terminal velocity, they define it as negative g over k, where k is, again, a constant given in the problem from your drag coefficient. And that's just the problem you can go through. But again, the analysis is the exact same. It's just you're doing it with gravity as well, because that was just the 1 dimensions, and this is the same thing. So okay, so now that we know that, you can do the exact same thing in 2 dimensions. So let's screenshot the classic canonical example of two-dimensional analysis, where what I like to do, as always, is you have your x and your y components, right? And from then on, it's just analysis. So let's treat the projectile in 2 dimensions. So in the x direction, we have 0 is equal to mx double dot. In the y direction, we have negative mg is equal to my double dot, right? So this immediately tells us then that x double dot is equal to 0. So x prime is equal to v naught cosine theta. That's just v, right? It's this component right there. And then x is equal to v naught t cosine theta. And you can just get these from your regular equations as well. But and we're also assuming like this height right here is 0, like it's sufficiently small. Now for the y direction, right, we have y double prime is equal to negative g. Integrate that once. Y prime is equal to negative gt plus v naught sine theta. Y is equal to negative gt squared over 2 plus v naught t sine theta. And these are just your general equations that you'll see of like delta x is equal to v naught t plus 1/2 at squared. You'll just notice this, and this is how it comes from. So we can now calculate the speed and total displacement as functions of time by noting that the velocity, or the magnitude of velocity, speed, is equal to the square root of x prime squared plus y prime squared, which is equal to v squared naught plus g squared t squared minus 2 v naught gt sine theta square rooted. And therefore r, again, magnitude of r, not the vector, is just equal to x squared plus y squared. And that's just equal to v squared naught t squared plus g squared t squared over 4 minus v naught gt cubed sine theta. Okay. And then you can find the range equations and whatnot by setting 0 for the final y value to get the range, right? So y is equal to t negative gt over 2 plus v naught sine theta is equal to 0. So therefore, the range is equal to v naught squared over g sine theta cosine theta times 2, where this right here just goes to sine of 2 theta. You can look in the textbook for the full derivation of that, but I just don't think it's worth going over because this is something you've probably seen before in your lower division classes. Again, it's just basically doing algebra. But okay, let's skip the rest of these examples since they're all pretty similar. Oh, and let's get into the perturbation method, which, interesting that you learn it here. I didn't realize that. I first saw the perturbation method in quantum mechanics. I guess I kind of took things kind of out of order. So let's quickly go over that. So the perturbation method, which the idea basically is you want to find something that is pretty small and then just perturb it. In other words, see what happens if you vary it a bit. Vary a small parameter, basically. So what we're going to do in the first case is we're talking about a retarding force with a constant k, right? So we have a constant k, and we've already solved the problem when k is 0. In other words, the retarding force is not there. But now we want to turn on the retarding force. So basically we solve the problem with no drag or whatever, no air resistance. And now I want to turn on air resistance. So we can model it as turning on k. In other words, we're perturbing our original equation. So we can start with the kinetic energy. Well, the kinetic energy is equal to kV plus g over gk, where k again is our constant, kt minus 1/2 k squared t squared plus 1/6 k cubed t cubed minus ... So in other words, we're just expanding in terms of k. And this is kind of the point of what's it called, perturbation method. So now what we want to do is basically simplify and choose what order we keep up to. So let's keep only up to k cubed. So we can get basically t is equal to 2v over g 1 plus kv over g plus 1/3 kt squared. We just get that by dividing out, basically. And now we have the expansion parameter k in the denominator of the first term on the right-hand side of the equation. So we need to expand this term basically in a Taylor series. So we can basically write 1 over 1 plus kv over g. And remember, we're expanding this because we're assuming this right here is really small. So we're doing the 1 over 1 plus x expansion, okay, as an aside, and that's just 1 minus, right? 1 minus kv over g, just like if this was a minus sign here, it'd be 1 plus, right? Plus, kv over g squared minus dot dot dot, because it oscillates. Okay, that means like we can rewrite our equation after our expansion as 2v over g plus t squared over 3 minus 2v squared over g squared k plus, some correction of order k squared. And basically almost always you just neglect this because we're just doing it to first order. So we can basically now calculate t when k is equal to 0. Well, that's just t naught, which we kind of already know is 2v over g, so this goes to 0, because it's all multiplied by k, right? Which is just 2v naught sine theta over g. As a reminder, v was just v naught sine theta because it's the velocity in our x direction, y direction. Sorry, we're doing the y direction. Okay, so now we can kind of rewrite our equation from 2.43, which is this right here. We can rewrite that in terms of basically for x. So x is equal to the potential divided by k, kt minus 1/2 k squared t squared plus 1/6 k cubed t cubed. So it's basically the same equation. But we know that x at t is equal to big T, where big T is basically the time until impact, right? Well, that's just our range, right? And basically then our range is approximately our potential, T minus 1/2 kt squared. And again, we're only going to keep, and again, there's more terms here, but we're neglecting terms of order higher than k because we already did so over here. Or over here, sorry. But yeah. Okay. So since we're only returning what's it called, first order terms or linear terms, we have 2uv divided by g, 1 minus 4 kv over 3g. And now we can rewrite this as, again, starting from here, 2uv over g is equal to 2v naught squared over g, sine theta, cosine theta, or sine 2 theta, whatever you want, which is just v naught squared over g sine 2 theta, which is our range equation. Since we know that, right there, since we know that 2uv over g is equal to that, then we know our new prime range equation is equal to our original range, 1 minus 4 kv over 3g, and that's our perturbation. Well, that's the analysis of our perturbation. That's how our, what's it called, drag force, or I guess retarding force, affects it. So what we want to do now is kind of analyze it, and we kind of know that our expansion in 2.48, which was 1 over 1 plus kv over g, does not converge if kv over g is greater than 1, basically, I think. Yeah, if kv over g is greater than 1, no, or equal to 1, no converge, because you need this to be smaller than 1, because of that Taylor series expansion. So that immediately tells us then that k has to be less than g over v, right? And if we want an accurate approximation, then we really want k to be much, much less than g over v, which is equal to g over v naught sine theta. Now, you can also solve this with the numerical method, which is just basically you put in a calculator, you put it in a computer, and it just does it via iteration until it converges, and it's the same thing. But okay, so now we kind of see how retarding forces affect it, and a little bit of a foray into the perturbation method, where it's basically just you just do a Taylor series approximation. But okay, so a lot more examples of like the Atwood machine. I'm sure that you've seen this before, and I guess for the sake of time, maybe I will go over it just because it's a good problem. But I'll just go over it quickly by just screenshotting the textbook. so I don't have to give my hand a little bit of a break from writing. So I'll screenshot the rest later. Basically, we write our equations of motion, right? And remember, the T's are equal because the rope basically just transfers the force. That's how tension works. Because the string is inextensible. Okay, that's, I guess, another way of saying the same thing, because it's an ideal string. But I don't know why my highlighter is not working either. Whatever, right here. That immediately tells us then that the accelerations are equal but opposite, and then we basically can solve and find out exactly how they equal each other, and then we can solve for tension. And this is an equation you guys have definitely seen before and have gotten. So that's basically for case A, where there's no elevator. So it's just a simple Atwood machine, right? But now what happens if we add an elevator and some stuff is fixed, basically? Well, in this case, right, it's a little bit more complicated, but not really. And the result simplifies pretty nicely. So we have m1 x1 double prime is equal to m1 x double prime plus x1 prime is equal to m1g. But we're in an inertial system, so remember, x1 double prime is equal to x1 plus x1, so you just add x1 prime plus x1. So you're basically adding the two together. And then same for x2. And that's why we do that here. We basically just change the double prime to the single prime and the non-prime. And then it's just the exact same equations we had before. But in this case, basically what's happening is when solving, we basically have this alpha component, right, which is, where is the problem again? Yeah, okay, alpha. I don't know why they used alpha. I guess whatever, so don't confuse you. I thought it was an A. It's just the acceleration of the elevator, basically. So let me write that on the side so it's not confusing. Alpha is acceleration. And then we basically just we get the exact same result as before, but it's the difference of the two accelerations. And you can get this exact same result just by treating it as just one entire system and noting that in an inertial reference frame, they just add, basically. Yeah, okay. So I think that was a good example of equations of motions for a particle. I could go over the magnetic one too. It's a good example, but let me see how much longer it is in this. I'll skip it for now. But if you haven't taken an electromagnetics course, I highly recommend you do it, because it kind of shows you how to do stuff in 3 dimensions and how basically the Lorentz force or magnetic force, whatever, QV cross B changes. And it's a good practice from chapter 1 with all the mathematics you need. But for now, let's skip that. So we can move into 2.5, which is our conservation theorems. Let me make sure my class is not until later. Okay, conservation theorems. So yeah, I'm a student, sorry. I'm just doing this for, studying basically for this class. So conservation theorems, well, I did say we would go back to linear momentum, right? To the conservation of momentum. So the first of the conservation theorems concerns linear momentum and basically tells us that if the particle is free, in other words, has no force, external force, or no force at all, P has to be a constant vector in time. So that basically tells us the total linear momentum P of a particle, P bold is the same way as write P with a vector arrow on top, is conserved when the total force on it is 0. This is derived from the fact that P dot is equal to 0. And therefore applies for each component of linear momentum. In other words, we can say that if we have some constant vector S, if F dot S is equal to 0, independent of time, then P dot S is equal to F dot S, which is equal to 0, because, P dot, right, because F is equal to P dot, basically, from Newton's second law. That tells us that P dot S is equal to a constant if you integrate this equation, right? because you basically get, you integrate this, you get p dot s basically, you get plus c, so it's equal to a constant. But okay, so now we can talk about, that's linear momentum. What about angular momentum? Well, angular momentum is defined as the vector L, which is equal to r vector, your position vector, across your momentum vector. And then we can also define torque, which I dislike they use n, but I mean, I guess they know better than I do. So torque is equal to n, I guess, which is defined as r vector across your force vector, which you might know as RF sine theta in lower division classes. But that lets us tell us then that n is equal to, or torque is equal to r cross mv dot, so ma, which is equal to r cross p dot. So therefore L dot is equal to the time derivative, right, of r cross p from here. I might drop the arrows soon because it's getting annoying to write it. Is equal to r dot cross p, again these are vectors, plus r cross p dot from chain rule basically. Therefore we also know that r dot cross p is equal to r cross mv, which is equal to m r dot cross r dot, which is equal to 0. In other words, this is telling us, since we know that we're crossing r, the derivative of r, time derivative of r with p, same as the basically crossing time derivative of r with v, well that's just crossing v with v, right? So therefore it has to be 0. In other words, that tells us then that L dot has to equal r cross p dot, which is equal to n. In other words, the time derivative of angular momentum is our torque. So that kind of tells us then that if no torques act on a particle, L dot is equal to 0. Therefore, L is constant. In other words, conserved, and that's the point. So, kind of like in linear momentum, if there's no outside forces, it's conserved. Well, same story in angular case, right? Angular is just basically always the same thing as linear, or very similar. It's almost always a one-to-one mapping. Okay, now we can define the work caused by a force. Let's say the work from point 1 to 2 is equal to the, from 1 to 2, if we're integrating of f dot dr, which if we look into what f dot dr is, f dot dr, again I'm dropping the arrows, m dv dt times dr dt times dt, which is just equal to m dv dt times v dt, which is just equal to m over 2 d dt of v dotted into v, which is just v squared, dt, which is equal to m over 2 d dt of v squared dt, which is just equal to d 1/2 mv squared. Well, wait a minute, that's kinetic energy. In other words, work is equal to the change in kinetic energy. So that tells us the work from 1 to 2 is equal to T2 minus T1, or delta T, where T is kinetic energy. Okay. Now we can also define it as basically the change in potential energy from the capacity to do work. So again, we have the integral of 1 to 2 of f dot dr. With the exact same analysis, we can get u1 minus u2. Notice it's u1 minus u2, not t2 minus t1, because it's equal to negative delta u. Because you need work to gain energy, right? You need to put in work to gain energy. Okay. As an example, here, let me see if somehow. Sure, we'll use this example. So let's say we have point 1 and point 2, and we notice 3 different paths, right? So an example, from position 1 to position 2, we can lift a suitcase from the ground. And we are doing work to do that, right? But there's different paths we can take. I can lift it up over my head, then put it back down into the trunk, or I can just barely do the bare minimum and move it there. So yeah. So now, what we kind of know is that if let the force and equation 2.87, this is 2.87, be negative. So let's say F is negative F. Therefore, F dot dr is negative, right? So therefore, u1 minus u2 is negative, or therefore the change in u is equal to the negative of the work done by gravity, right? So we can reproduce this and write this in a more general way by defining the force as equal to the negative gradient of the potential energy, which is a scalar function. So this immediately tells us then that integral from 1 to 2 of f dot dr is equal to negative integral from 1 to 2 of gradient of u dot dr, which is just equal to negative 1 to 2 du, which is equal to u1 minus u2, right? Because this integral gives us u2 minus u1. Well, that's just u1 minus u2 if you put a negative. And I guess they want to make an important note, and I do as well. Notice that u is a scalar function. So potential energy is never defined absolutely. If it's not mentioned, it's always assumed that the potential at infinity is 0. But basically, it's always defined relative to a point. Because no matter where I am, that could be anywhere in the universe, Earth's gravitational field and the potential energy I have from Earth is always there. It's just when I'm super far away, it doesn't matter because it's basically 0. In other words, potential energy has no absolute meaning. Only differences in potential energy are useful because that's what gives us our energy, right? Or work. That immediately tells us that the total energy of a particle is equal to basically the sum of the energies, right? You can have some kinetic and some potential. If we take the time derivative of this, well, that's just the time derivative of each, right? And again, if we write f dot dr, well, that's just d 1/2 mv squared. That's just equal to dt, right? And we could divide through by dt, and we get dt is equal to f dot dr dt. Well, that's just equal to f dot r dot. And since we also know that du dt is equal to f dot dr dt, well, that's f dot r dot. Oops, sorry, wrong equation. I got sidetracked. Sorry. Du dt is equal to basically the sum of the partials, du dxi, sum over I of dxi dt plus whatever you start from, right? That's your initial condition. Well, that's just basically equal to our gradient of u dotted into r dot from our analysis above, plus our starting point again. These are partials, by the way. Pardon my bad handwriting. So therefore, if we go back to dE dt down here, we have dE dt is equal to f dot r dot plus gradient of u dotted into r dot plus our starting or our relative function, which if we can put it in the dot, because again from chapter 1 we know the dot product is it distributes, so f plus gradient of u dotted into r plus del u del t. Well, that lets us know that basically we can set the is that a row? Hold up. We find that they say rho is equal to del u del t, or I guess rho is just our answer, basically, of del E del T. It's just our power. It's our power, my bad. I don't know why these are lowercase p. I've always seen uppercase. Our power is because power is in watts. And watts and energy is joules, and watt is equal to joules per second. So yeah, so our power is del U del T, and what we immediately notice is that it doesn't vary in time because... No, you suck. Aren't you working? Where's black? There's black. Anyways, because this function right here, right? It's a scalar product, right? So that's a number, so it's basically so dE dt is constant. So let me write this as something that's probably more clear. dE dt is equal to constant. Which our constant is del U del T because, remember, F is equal to negative gradient U. So this right here, which I can't switch, is 0. Right? Okay. In other words, the total energy of a particle in a conservative force field is constant in time. Okay. Good. So we've kind of been talking about energy, but let's do a more deep dive in it. So 2.6 brings us to the conservation, or to the conversation of energy. Sorry. So let's consider a point particle under influence of a conservative force with a potential U. So therefore, our total energy equation, right, is E is equal to T plus U, which is just 1/2 mv squared plus our potential, which we'll say is a function of position. So our velocity, in this case, is equal to dx dt, which is equal to plus or minus, remember we're rewriting it because we had v here, square root 2 over m e minus u of x. And wow, this looks eerily similar to a lot of stuff you'll do in quantum mechanics with particle in the box and how potentials can shift. If you have like a step potential or something, and that goes to show that quantum mechanics is really just applying classical mechanics with a few key differences of like quantization of energy and stuff. That's not continuous. But anyways, that immediately tells us then that if we integrate this, right, t minus t naught is equal to the integral of x naught to x plus or minus dx, and then all this over here, right? Because we just brought that over like so, and then brought this over here, and then brought this over there. So that tells that over 2 over m e minus u of x, and then we basically solved the one-dimensional case. But the problem is, problems are usually three-dimensional, so it's a little bit more complicated normally. But yeah, later on we'll see some kind of different kind of potentials. Like for example, if you have a quadratic potential, like for example u is equal to 1/2 kx squared, that's called a harmonic, and we'll see why. Or u is equal to negative k over x, well, that's gravitational, right? Because gravitational is just linear. Or no, not linear, sorry. It's a 1 over r relationship, which you might already know, spoiler alert, from Newton's gravitational law, which is g/mm over r squared. But yeah, anyways, let's ignore that for now, and let's keep going. And here, I'll show you their graph for some various potential energies of different values of E. If I can paste, which, okay, I did. Here we have our potential energy function, scalar function again. Remember, energy is also scalar. And then we have our different positions. We can notice, right, for example, E1 and E2, the motion is bounded. In other words, if you jump from energy 1 to energy 2, you're stuck in this potential well, you can't get out. But if you have enough energy to hit E3, boom, you can jump out, and then you can escape this way. And then E4, well, you're not bounded anywhere, right? So A particle with energy barely above E naught will oscillate about the point x is equal to x naught. So here's E naught, in other words, our base energy of the system. And if you're stuck here, you can imagine like a skateboarder, you just go up and down like this, and then so forth for the other ones as well until you have enough energy to actually escape the ball. Yeah. So we can usually express, or in general, we can express the potential energy as a Taylor expansion. So we can expand U of x as just, this is just a general Taylor series plus x, I guess I'll write it long. I would just write x prime, 0 plus x squared over 2 factorial, d squared u dx squared dot 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 plus dot dot dot. And you can go third power and fourth power, whatever. And basically, this subscript 0 means evaluated at 0. So let me write it like that. Evaluated at 0. At x equals 0. Sorry. And if x is equal to 0 as an equilibrium point, then we know that du dx at 0 is equal to 0. So therefore, u of x is equal to x squared over 2 factorial d squared u dx squared, because this goes away, right? And if we assume u not to be 0 as well, because we can define it to be 0, because again, the only thing that matters, right, is the difference. So if we just define this to be 0, this right here gives us the difference immediately, right? Okay, so now that we know that the second derivative is the important one, basically we need to determine if it's stable or unstable by examining this right here. And this, of course, has the plus other terms of Taylor series expansion. So if the second derivative of 0 is greater than 0, stable, yay, we're done. If it's less than 0, unstable. And we can actually immediately see this from the graph. So second derivative tells us concavity. If the second derivative is greater than 0, boom. If we're here, it's stable. Like right here, it's stable. If it's less than 0, unstable, because of the concavity. So you want to basically stay in that well. But okay. Then there's more examples, and then I guess we can briefly talk about the limitations and then wrap up for today. So there's other examples in the textbook we can go over, but let's just briefly go over some limitations of Newtonian mechanics, which I've kind of already alluded to. A great example would be light. Like the if you have inertial reference frames and you basically want to see how fast is a person not standing in the train see light move across the train versus the person in the train, and you'll find out that if both try to measure it, they'll both go at the same time. And that's because of, but you won't with Newtonian physics, because for Newtonian physics the train is moving with like v is equal to 10 meters per second and light is 3 e to the 8. Therefore person sees light go at 3 e to the 8 plus 10, and that's not the speed of light. So that's wrong. This is bogus. But it works for a lot of cases because we don't have to deal with relativistic stuff for a lot of times. Let's see. Oh, this is exactly what they talk about. They talk about the wave character of the photon precludes an exact measurement. This is related to the Heisenberg uncertainty principle, which you'll find out basically tells you can't know with certainty both the position and momentum of an object. It's like something like delta x, delta p has to be greater than or equal h bar over 2. I'm paraphrasing here, that might be wrong. But that's basically the Heisenberg uncertainty principle. It's some factor like that. Which basically tells us we cannot know, like basically if you know one, you can't know the other fully. Oh, they do mention the Heisenberg uncertainty principle. Perfect. So basically, kind of just this last section is basically just telling you that, just so you know, not all of this is actually right. This works for a lot of good Newtonian systems, but there are clear-cut limitations where we need new physics, basically. And that's why Einstein got so much. Good. I don't know if you guys can see those text messages. Hopefully not. But she's better than average on physics. So let's go. Woo! I guess tutoring helped. Anyways, it was dope doing this, and we'll be back with chapter 3 sometime soon. See you guys.